write the following system of equation as a matrix equation of the form AX is equal to B. So we want to turn this system into a matrix equation of this form. So let's try to do this one. So here's the system that we are given: 3x sub 1 plus 2x sub 2 plus x sub 3 equals to 5, x sub 1 minus 2x sub 2 plus 5x sub 3 equals to negative 2, 2x sub 1 plus x sub 2 minus 3x sub 2 equals to 1. So if you want to turn this one in terms of matrix equation of the form AX is equal to B, that's what we want to do. So first, the A represents an augmented coefficient, no, a coefficient matrix. So A is going to be the coefficient of all of these. So 3, 1, 2, 2, negative 2, 1, 1, 5, negative 3. That's A. Now, X will represent the vector of solution. So the vector of solution will be the vector that has a solution as values x1, x2, and x3. So that vector X is this one over here. And B is basically the right-hand side of our system. And that's it. So we're able to turn this one into a matrix equation of the form X is equal to B. Now,
sir. So we are done.
Yes, it's over. Yeah, the question is over.
Okay, no problem.
So if, for example, if you are given this and they were asking you to turn this into a system, then you have to use it's like multiplication. It's like you have to do the multiplication, like this times this one, just like in the previous example. This times that one, this one times that one, and you'll obtain this one over here. But what you're asking is, given this, you want that. So that's what we've done.
Okay.
So if you assume, if we consider that we have like a m by n linear system like this, a11 x1 plus a12 x2 plus a1n xn equals to b1. We have a21 x1 plus a22 x2 plus plus an 2n xn equals to b2 am1 x1 plus am2 x2 plus plus amn xn equals to bm. Let's assume that we have a m by n system. What we can do using this system is to we can represent this system in terms of a matrix equation, in terms of AX. In terms of a matrix equation. And if we do that, this is what we'll get. We can turn this this part of the matrix, this part, in terms of a matrix equation. So let's try to do that. Let's try to find AX. So the coefficients and the x's. So if we were to write it down, we'll have the following in terms of a matrix equation: a11 x1 plus a12 x2 plus plus a1n xn, a21 x1 plus a22 x2 plus plus a2n xn, am1 x1 plus am2 x2 plus plus a mn xn. So we turn this one into a system. Now let's think about it. There is another way we can represent it. One step further. There's another way we can represent this, is by looking at these x's over here. You notice that they have x1 over here, right? Okay. Notice that you have x sub 1 over here. You have x sub 2 over here. You have x sub n over here. So what you can do is you can kind of like factoring the x1 out. So it's like you have x sub 1 outside here, and then you copy the column vectors x a sub 1 1, a sub 2 1, dot 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 a and 1. You copy the plus sign that is in the middle. You have x sub 2, x sub 2, x sub 2. So you kind of factor out the x sub 2s, and you have your column vector a12, a22, dot 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 a m2. So you continue the same process m times, m times, and then you have x sub n. So you can factor out x sub n out of this column, and you have a1n, a2n, dot 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 amn, like this. So your matrix can be written as a like a linear combination, a combination of coefficients. So here it's not a vector. Here it's a number. X sub 1 is like will be a number like not your solution. And but this one is a vector, a column vector. This one is a column vector. This one is a column vector. So in other words, you can turn your matrix into a linear combination, a combinations of column vectors. Okay, you can transform your system, your linear system, or your matrix in terms of combinations of column vectors. So let me write this one in terms of vectors. So x1 times this column vector, let me change the color. x1 times the column vector a1, yeah, plus x2 plus the column vector a2 plus dot 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 plus xn. I don't know if you can see xn times the column vector an. Okay, so we have now we can represent we can express our matrix equation in our matrix equation as a sum of column vectors. Okay, so that's another representation. So in other words, we can have ax is equal to this, and that is also equal to b. Okay, so let's go back to the note. Okay, I think we've already solved this one. Write the following system of equation as a matrix equation of the form x is equal to b. That was already solved. So now consider an n by n linear system. Okay. Now, an alternative way to represent this linear system as a matrix equation is to express the product AX as a sum of column vectors. So here's our matrix equation, and we turn it in terms of column vectors as a sum of column vectors. Thus, we have the matrix A times the column vector X is equal to X sub 1 times the column vector A1 plus A sub 2 times the column vector A2 plus dot 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 plus X sub n times the column vector an. Using this formula, we can represent the system of linear equation as a matrix equation of the form a sub x sub 1 a1 plus x sub 2 a2 equals to b. Now write the following system as a sum of column of a matrix equation. So write the following linear system as the sum of columns of a matrix equation. So let's do that. As you can see, you can easily see that we have x1 over here. I can factor out x1, x2 over here. I can factor out x2. So let's do it on paper. So we have this system 2x1, 5x2, 5x 5x sub 1 here plus 3x sub 2 minus 2x sub 3 equals to 5, negative 4x sub 2 plus 2x sub 3 equals to 6. Now I can see that I have my x1 over here. I can factor out my x sub 1 and I copy the column vector that is left to 5. I will put a plus sign. These will be just coefficients. I have x2 over here, x sub 2. I can factor out x sub 2. And I copy the column that I'm seeing here, 3, negative 4. I have my x3 plus x sub 3. And I factor out my x sub 3. And then I copy the columns that I have. And that is equal to 5, 6. That's it. Okay. So we can represent this system that is here into this form. This is another way of representing this system, and it's this system in terms of column of sum of column vectors. Okay. So any questions related to this one? So let's move. So definition, if notice that when you write capital letter like bold face letter a sub 1, we're meaning column vector a sub 1. Now if you write it with an arrow on the top, it means row vector a sub 1. So if a sub 1, a sub 2, a sub n are vectors in Rm, and c sub 1, c sub 2, c sub n are scalars, then the sum of the form c sub 1 a sub 1 plus c sub 2 a sub 2 plus c sub n a sub n is said to be a linear combinations of the vector a1, a2, and an. So what we've seen so far, what we just did, so it follows from, so what we just did in the previous example was what we call a linear combination. When you have when you write in terms of x1 multiplied by a column vector plus x sub 2 times another column vector, that combinations of column vector is what we associated with a certain number is what we call a linear combination. So it follows from ax equals to x sub 1 a sub 1 plus x sub 2 a sub 2 plus plus x sub n a sub n, that the product ax is a linear combination of the column vectors of A. So if A is a m by n matrix and x is a vector in Rn, then Ax is equal to x sub 1 a1 plus x sub 2 a2 plus plus x sub n an. Okay. So let's see an example of that. So what we want to do is just to write this one in terms of a linear combination. And once we've turned it into in terms of linear combination, we're going to choose x sub 1 is equal to 2, x sub 3 is equal to x sub 2 is equal to 3, and then x sub 3 is equal to 4. So let's turn this one in terms of linear combination. So write the above linear system as the sum of columns of a matrix equation. So the way I think we already have, so here we can say let's write, let me write here. We have 2x sub 1, 2x sub 1 plus 3x sub 2 minus 2x sub 3 equals to 5, 5x sub 1 minus 4x sub 2 plus 2x sub 3 equals to 6. What we want to, let's write this system as the sum of columns of a matrix equation, or as a linear combination of column vectors. Okay. So we have x sub 1 is equal time plus x sub 2, 3 negative 4 plus x sub 3 negative 2, 2 equals to 5, and then 6. Now what we want to see, if we choose x sub 1 equals to 2, x sub 2 equals to 3, and x sub 3 equals to 4, if we choose these values, do we get this? That's what we want to know. So let's choose 2 times 2, 5 over here, plus plus 3, 3 negative 4, plus 4 negative 2. We want to verify if we select it, it's like you have a system like this, and what you do is just choosing like values 2, 3, 4, and see if you use these combination of values, do we get 5, 6? So how do we do that? So 2 times 2 is 4, and then the 2 that is here is going to be multiplied by the 5 also, is going to be 10. So here I have 2 times 2, and then 2 times 5. That's the first one. Plus the second one, 9 here, 3 times 3, 9. And here, 3 times negative 4, plus 4 times negative 2, 4 times 2. So 4 times 2 times 2 is 4, 2 times 5 is 10, 3 times 3 is 9, minus 12, negative 8. That's going to be 8. And then I'm going to add them up. Remember, for sum of vectors, you basically add them up. You add each corresponding entries. So here I'm gonna have 9 minus 1 is 9 minus 8 is 1. 1 plus 4, 5. Here I have 18. 18 minus 12 is 6. Okay, so if we choose 2, 3, and 4, and we plug into these combinations of numbers, and we plug it into these combinations of column vectors, we obtain 5 and 6. So we can see clearly that 2, 3, 4 are solutions to the system based on that, because they verify this equality. Okay, so so we can see that from this, we can see that 5, 6 is actually a linear combination of 3 column vectors of the coefficient matrix. So 5 is actually a linear combination of the column vectors of the original matrix, the coefficient matrix, and it follows that this system is consistent, and 2, 3, 4 is a solution to the system. So x1 is equal to this, thus the vector 5, 6 is a linear, so let me continue writing it over here, is a linear combination of the 3 column vectors of the coefficient matrix. And
So,
yes,
since this system is like underdetermined, it has an infinitely many solutions, right?
let's see. Yes,
Okay, okay.
But you guess x1, x2, and x3. So does it mean now we can give any value to x1, x2, and x3?
the reason, okay, your question is, I have guessed x1, x2, and x3, and
Mm-hmm.
does it mean that we have to always guess s1, x2, and x3?
Mm-hmm.
Okay, it's not always. Here, the point is not always. Normally, yeah, here like x1, x2, and x1, x2, and x3, like they were chosen. It's like we don't have to guess. Normally, we have to solve. Like the way we would normally solve row reduction. Well, that's what we need to do in order to find x1, x2, and x3. That's what we normally have to do. But in this particular case, what we're trying to do is to illustrate a point. And the point that we want to illustrate is that if you want, we want to illustrate the fact that we can write, like for a system to be consistent, we can write, if we are able to write it in terms of linear combination, then that system will be consistent. That's where we're trying to get to. But here, x1, x2, and x3 were chosen. Like it was like it's even in the problem. It's like these are points that are given to you already. But it doesn't mean that every time you have this kind of problem, you'll be choosing like values for x1, x2, and x3. No, you will not be choosing. Usually, you will be solving as the the way we solved for the previous type of system. But what we want to do is to looking at what our goal is to look at it from a different perspective. If we are able to write it in terms of linear combination like this, we can, and those linear combination have like if you pick up values for these x1, x2, and x3, and you find a solution, then you can say that the system is consistent. Okay, so it's like we are trying to get to a point where we will be saying if we are able to write the system in terms of linear combination, then the following consequence is going to happen. Okay, so the values that were chosen here, we're not going to choose it every time like this. No, what we're going to be doing is to, it's like here we're trying to illustrate a point. Okay, I don't know if, okay, but the key things that we need to remember, we're not going to be choosing this every time. No. Okay, this is the
Okay, sir.
essential point, yeah. So, okay, so this is like the linear combinations. So the vector 5, 6, 5, 6 that is here is a linear combination of 3 column vectors. This is one column vector, another column vector, another column vector. So that vector can be written as like a combination, a linear combination of 3 other column vectors of the coefficient matrix. And the solution, the vector solution x, x is actually a solution. X with entries 2, 3, and 4, 2, 3, and 4 is a solution of the system. Okay, so that vector is actually a solution of the system. So that leads us to a theorem. So this consistency theorem for a linear system. So from that we can say that, like in general, so from this situation, we can generalize it, say that if you have a system of the form ax equals to b like this system is consistent if and only if b can be written as a linear combination of the column vectors of a. So that's so from this example, we draw, like we can say that, you can say that if you have a linear system of equation and the right hand side, if that right hand side of that system can be written as a linear combination of the columns of your coefficient matrix, then you are dealing with a system that is consistent. Now, if you're trying to write these columns, if you cannot find a linear combination of values that gives you that b, then the system is inconsistent. Okay, so that's what this theorem is actually meaning. Let's go back to the note. So theorem, consistency theorem for linear systems. A linear system AX is equal to B is consistent if and only if B can be written as a linear combination of the column vectors of A. So is the following system, is a linear system below consistent? So let's try to solve this one. If we want to know if the linear system below is consistent. So let's try to do this one. So normally I should be like solving like row reduced echelon form, things like that. But I'm just trying to use a different path. So you have something like that, x1 plus 2x2 equals to 1, and 2x1 plus 4x2 equals to 1. So x1, 1, 2 plus x2, 2, 4 equals to 1, 1. The question is, can you find, like, what number can you plug over here and here that would, what's the number that you need to plug here and here such that you get 1 and 1, okay? And if you are able to find those two numbers and you get 1 and 1 over here, that means the system is consistent. But if for whatever number, let's say I take 0 and 0 here, I don't get 1, 1. If I take 1, 0 over here, I get 1, 2. If I, like for any number that I'm trying to plug, if I find 1, 1, then I can say that the system is consistent. But for this one, it's simple. The linear system is inconsistent since 1, 1 cannot be written as a linear combination of the vectors 1, 2 and 2, 4. So there is no way you can plug a numbers here and here so that you'll obtain 1 and 1. So in that case, you can easily say that the system is inconsistent. Now, if you are able to find a combination of x1 and x2 that gives you 1 and 1 here, then you will say that it is consistent.
Sir?
Yes.
So if I understand, if we are given a situation like this,
yes,
we'll plug these column vectors into like linear systems of equation as we did, and we'll try to find a solution.
You want to turn it will take
like to get the x1 and x2s.
Mm-hmm.
We will have to plug all this into a linear system of equation and solve it, right?
It depends. Let me explain what I mean by it depends. Sometimes sometimes you'll be using row reduced echelon form.
Mm-hmm.
Okay. Sometimes this one is faster than row reduced echelon form. Sometimes this way is faster than using row reduced echelon form. So that's what I'm saying. It depends on what you have in front of you. Typically, when it is inconsistent, it's row reduced echelon form that is faster because you can easily draw. You can do your system, do the reduction. You can see that 0 is equal to 1 or something like that. Then it's inconsistent. Sometimes this one is extremely easy. Sometimes you'll see something like that. 1, 2, you'll see, let's say, that's like, let me think about something that's extremely easy. Let me try something that is extremely easy. Maybe, okay, this one is kind of like extremely easy.
Yeah, it's
Okay.
consistent.
So here, like, you know that in order for you to get like 1, 2 over here, if you take x as 1 and x2 as 0, then you have this. Because if you take 1 times this one, you have 1, 2 plus 0 times this one. And if you add them up, you have 1, 2. Okay? So in that case, you can easily see that it is consistent. Okay, so sometimes using row reduced echelon form is faster. Sometimes just by looking like this with your eyes, you can
Like
see,
guessing, sir.
yeah, by guessing, yeah.
Okay,
You
no
can
problem.
easily see that it's easy. So you can easily see that it's inconsistent. No, it is
Okay,
consistent, and then you move on.
okay, sir.
Okay.
No problem. Okay, sir. Thank you.
So okay, so in this case, this linear system is inconsistent since one cannot be written as a linear combination of vectors 1, 2, and 2, 4. Okay. So next, okay, I don't, okay. So sometimes for multiplications of matrices, So for example, what you can do when you have, like, let's say that you have a matrix A multiplied by another matrix B. Now, you can write this product as A time the columns of B. Okay, so it's like, so B, okay, B can be expressed as the following. B, that matrix can be expressed as B sub 1 in terms of columns, right? So B sub 1 in terms of column vector, B sub 2 that time, let's say, goes to B sub n. So it can be represented, this matrix B can be represented in terms of column vectors, or it can also be represented in terms of row vectors. So the point of this part is that if you have a product A times B, you can write it as matrix A times the column vector B1, matrix A again times the column vector B2, dot, 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 matrix A times the column vector B sub n, like this. And once you do that, so now you have to do this matrix times this column vector, this matrix times this column vector to find the result. The other way is to think about this. This is one way. One way to calculate the product. Another way will be to, let's say you have like matrix A in terms of Aij and matrix B in terms of Bij, and in matrix C, which is equal to, in terms of, another notation for this is this. Now, we can, if we have C equals to A times B, the Cij entry of that matrix C is going to be equal to the sum of the it's going to be first, so the Cij entry of, okay, let me write it in terms of matrix first. Let me do it this way. Let's do it simply. Let's say I have my matrix A with entries 1 1, A1 1, and A2 1, and A1 2, and A2 2. This is my matrix A. My matrix B is the following: B1, 1, B2, 1, B1, 2, and B2, 2. And what we're saying is that A times B is supposed to equal to a matrix C. A matrix C has entry C1, 1, C2, 1, C2, 2, and then C1, 2, and C2, 2. So this entry over here, what does it equal to? So the C11 that is here is equal to this row times the scalar product of this row and this column over here, and we obtain the first column over here. So in other words, so C11 will be equal to the following: A11, A12, B11, B21, like this. Okay, so it's like a scalar product, and it's this times that plus this times this. So we can kind of generalize this formula over here. So it's as if it is a sum. It is a sum, okay, of A1, because we are dealing with C1. So A1. So let's observe the pattern. What is changing and what is not changing. So here, the value here is here we have A11, here we have A21, 1, 2. So here what is changing is the 1 over here, and the 2 over here is changing. The 1 over here is changing, and yeah, the 1 over here is changing, and the 2 it turns into a 2. Okay, so I can write A1 is not changing, the A1 is not changing here, B1 over here is not changing, so A1 here is not changing, B1 over here is not changing. Now the second one that is here is what is changing. Okay, so it goes from let me call it K, and here let me call it a K over here. Okay, so it's the sum of the product, because we have a product over here of A and B, such that the entry, like it is the values that are changing across the row of the column of A is changing, but and the row of B is changing. So that is what is happening over here. The row of A is changing, the column of B is changing. No, it's the other way around. The column of A is changing, the row of A is changing. So it's like the sum A goes from 1 to N being like row of A. At the same time, it's the column of A, number of column of A, and the number of row of B. Okay, so it's like we are dealing with a sum of K going from 1 to N of the product of A and B, such that we have this. Okay, here N is how much? How many data value do we have here? We have two rows, so no, 2 columns. So here 2. So in other words, C11 equals to the sum of K going from 1 to 2 of A1 K B K1, like this. And yes, so that is like for the case C11. Now let's generalize further. So for Cij, Okay, I'm changing 1 and 1 here to I and J. So for Cij, I will have the following. So the only thing that is changing here is going to be I and J. So the same formula, sum k goes from 1 to n of A, I, K, B, K, J. Okay, so in general, so for a matrix A and a matrix B, such that A times B is equal to another matrix C, the IGF entry of that matrix C is equal to the sum of the A entry, A sub I entry, K times B sub K J entries. So this is like the generalization of this formula. Okay, but but to make it simple, if you want to find, for example, this entry, you do this one times this one, it gives you that one. If you want to find this entry over here, if you want to find this entry over here, you take this row, multiply by this column over here, and it gives you the value over here. You want to find the value over here, you take this row, multiply by this column, you obtain this value over here. You want to find this one over here, you take this row times this column to find this entry. If you want to write this information in terms of math, this is what it would look like. Okay, the CIGF entry of the matrix C is going to be the sum product of A sub IK multiplied by B sub KJ. Okay, so any questions related to that? So let's go back to the note. So before I move on, these are two ways of actually expressing the same thing. This A times B, you can, to find C, you can do this. A times B1, comma, A times B2, you can do that. Or you can use the term in terms of scalar product. You can write it in terms of scalar product like this. So matrix multiplication, more generally, it is possible. More generally, it's possible to multiply a matrix A times a matrix B if the number of columns of A equals to the number of rows of B. Okay, so remember this information. The number of columns of A has to be equal to the number of rows of B. The first column of the product is determined by the first column of B. That is, the first column of AB is A times B sub 1. The second column of AB is, and so on. Thus, the product AB is a matrix whose columns are A times B sub 1, A times B sub 2, A times B sub n. So the matrix AB can be written as, you take the matrix A, you take the first column of B, and then comma, the matrix A, for second column of B, etc. So the IGF entry of AB is the IF entry of the column vector, and A times B sub j. It is determined by multiplying the IF row vector of A times the JF column of the vector of B. So let's look at the definition. So if with entry A sub ij is a m by n matrix, and B is a B sub B with such that B is equal to, as entry B sub ij is a n by r matrix, then the product A times B is equal to M is the M by R matrix whose entries are defined by C sub ij equals to the row vector of A times the column vectors of B, such that we have a sum of rows and columns moving across the row of the first the column of the first matrix, and at the same time going across the rows of the second matrix. So basically like a a scalar product of the entries of A and B. So let's see an example. So if A is equal to this and B is equal to this, let's find AB. So let's do it the first way. We want to find the matrix AB. So A is equal to 3, 2, 1, negative 2, 4, negative 3, and B is equal to negative 2, 4, 1, 1, 3, 6. We want to find AB. So A times B, like I said, you take this row. So it's like if we are in here, we are dealing with a we are dealing with a row. So I'm doing row times column. Then let's say that I want to, for the values over here, let's say I want to find the values here, here, and here, these entries. Before I even do that, let's look at something. Here I have a 3 by 2. 3 by 2. Here I have a 2 rows, 3 columns. So I'm supposed to get those two cancel. I'm supposed to get a 3 by 3. That's what I'm supposed to get. Okay. So let's look at, so this AB that we're gonna get is gonna be a 3 by 3. So let's start with this one. I take this row times this column. Okay. So it's like I'm doing row 1 of the matrix A, this row 1 of matrix A, multiplied by the column 1 of the matrix B. Okay, and then here I'm going to do row 1, row 2. So if I want to find this entry over here, I go here to the row times column. Row 2, column of A, multiplied by row 2 of matrix A times the column, because I want to find the value here, time, this one is fixed. This one does not change. I take this times this, plug it here. I take this times this. This one does not change. I plug it here. Now to the third entry over here, I take this times this to have the value over here. So what is not changing is the column is not changing. Now if I'm moving to another column, I move to this column over here, then this one will be changing across the rows, but this one stay constant. This one does not move. If I go to the third column over here, to the values in this third column, I take this one and I plug it over here. This one, I plug it over this one times that one to the second entry, and then this one times this one to the last entry. So let's do that. So row 2 of column of matrix A times the column 1 of matrix B. Here I take row 3 of matrix A, multiply that by the column 1 of matrix B. Okay, that's what I'm going to do. Normally I should not write this. I'm just writing this for illustration purpose. So row 1 of A is like a scalar product. This times this. So I have 3 times negative 2, 3 times negative 2, plus negative 2 times 4, times 4. Now here, this times this one does not change because we are still in the first column. So 2 times the negative 2. So the first entry times the first entry plus the second entry times the second entry. Okay, now the third one over here is this one and that one. So this row times this column vector. So the first entry times the first entry plus the second entry times the second entry. So 1 here times negative 2 plus negative 3 times 4. Now I'm finished. I'm done with this column, this first column over here. Now moving to the second column over here. So for the second column, I'm no longer using this one. I'm using now this one, this one over here. So I take the first row here, um, row one of matrix A, multiplied by the column 2 of matrix B. Row 2 of matrix A multiplied by the column 2 of matrix B, and then row 3 of column A multiplied by the column 2 of matrix B. Okay, so I take okay, so this one times this one. So the first entry times the first entry, second entry times the plus second entry times the second entry. So I have 3 times 1, this time this, and then plus this time that, plus negative 2 times 1. Row 2 of matrix A times the second column of this matrix. So 2 times 1 plus 2 times 1 over here, 4 times 1. So I have 2 times 1 plus 4 times 1. Next is this one times that one. So 1 times 1 plus negative 3 times 1. So 1 times 1 plus negative 3 times 1. Now the third column, this column over here, gonna be this one times that one. So this vector times this vector. So 3 times 3 plus negative 2 times 6. So it's gonna be, let me write it in terms of formula, kind of. So row one of matrix 1 of matrix A times the third column of the matrix B. Row 2 of the matrix A times the third column of matrix B, and then row 3 of matrix A times the third column of matrix B. And that's going to be here row 1 matrix A. So 3 times, so this one here times this one. So 3 times 3 plus negative 2 times 6. So I get 3 times 3 plus negative 2 times 6. Next one is 2 times 3 plus 4 times 6. The third one is 1 times 3 plus negative 3 times 6. Okay. Okay. Now I'm going to write it down in terms of numbers. So negative 3 times 2 is 6, negative 6, negative 6, negative 8, negative 14. And 3 minus 2 is just 1. 6 minus 12 is going to be, let's see, 9. 9 minus 12 is negative 3. Negative 4, 8, 16, 12. Here, 2, 4, 6, 6, 24, 30, negative 2, negative 12, negative 14. Here it's 1, negative 3. So negative 3, negative 2. Negative 3 plus 1 is negative 2. 3 minus 18 is negative 15. So here I have my matrix, the product A times B. That's one way of doing it. Okay, so here's a result. So another way of doing it would be to okay, so I'm turning to the next page. Another way of doing it will be to use the formula. So here the formula that I've used is this one. Is actually Okay, this is the formula that I've used for this one, and I can add this one. Now I'm going to use A times B. A times B, A B1, A B2, A B3, according to the formula. Now I know that matrix A is 3, 2, 1, -2, 4, -3, and matrix B1. Okay, so let me write the matrix first. So the matrix that we had originally is 3, 2, 3, 2, 1, -2, 4, and -3. And the matrix B is -2, 4, 1, 1, 3, and then 6. Now, based on this matrix over here, my B1 is this one over here. This is B1, B sub 1. This is B2, and this is B3. Okay, so B is actually can be written as B1, B2, and then B3. Now, what I'm doing is taking matrix A, multiplying it by B1, which is that one, and then I put a comma. So that's what I'm going to do. B1, this is B1, -2 and 4, and then comma, A, matrix A, 3, 2, 1, -2, 4, and then -3. B2, B2 is this matrix 1, 1, comma, matrix A times B3. Matrix A, 3, 2, 1, -2, 4, -3. B3 is this one, 3, 1, 3, 6. So now, the way I break it down is, here I have this one times that one over here. And the way I'm going to do it is to take row times column, row times column, row times column. So here, there you go. You have this row times this column. The first row, so the first row, 3, -2, times this column vector, -2, 4. This row over here times this column, 2, 4 times -2, 4. And then this row times this column, 1, -3, and then the column -2, 4. So that represents the values in the first column. Now let's move on to the values in the second column. So what we're doing this matrix times this column over here. So the way we do it is to do a product of rows times the columns. So the rows that I have are this row, and that row. So I take this row, 3, 2, 3, -2, times this column, 1, 1. Now the second column, 2, 4, times this column, 1, 1. Now the next row, 1, -3, times this column, 1, 1. Now I'm done with this column over here. Well, these are all the entries of this column. Now let's look at the third column over here. So this row times this column. So 3, -2, and 3, 6. This row times this column, 2, 4, 3, 6. And then this row times this column, 1, -3, and 3, 6. Okay, now the way we do this product is basically, this is our traditional scalar product. So now I'm doing this times this plus this times that. So 3 times -2 plus -2 times 4. So the first entry here times the first entry plus the second entry times the second entry. Okay. And here, this time this plus this time that. Here, this time this plus this time that. This time this plus this time that. Now, to 1 times 1 plus negative 3 times 1. Here, 3 times 3 plus negative 2 times 6. And this times this, so 2 times 3 plus 4 times 6. And 1 times 3 plus negative 3 times 6. So if you do the calculation, you also get AB equals to negative 14, 12, negative 14, 1, 6, negative 2, negative 3, 30, and negative 15. Okay, so AB. So that's the second way. If you want to use this formula over here, you break it down in terms of columns. You break B, the second matrix that you have, in terms of columns. And once you write it in terms of columns, you break it further down in terms of row time columns. So row time columns, row time columns, row time columns. And after that, you do the scalar product, and then you find your answer. That's another way of doing it. Okay, so let's continue. So if you were to calculate B times A, you use the same process. If you were to calculate B, we found out that AB was negative 14, 12, negative 14, 1, 6, negative 2, negative 3, and then negative 15. Now, if you were calculating a BA, BA is going to give you, B is actually a 3 by 2, and A is a 2 by 2. You'll obtain those two can cancel a 3 by 2. That's what you're supposed to obtain. A matrix T. A new matrix has you enter 3 rows and 2 columns. So if you are calculating it ABA, you'll get something like 5, 8, 17, 26, 15, 24. So as you can see, AB is not the same as BA. Okay, so we can say that the product of matrices is not commutative. Okay, so that's what we can say about the product of matrices.
Okay, sir.
Yeah. Now there's something called the transpose of a matrix. Let's say that I have a matrix A. Now the transpose of a matrix should be denoted as A transpose, and the way you write it down is a T at the top. On the top, let's have a matrix. Let's say A equals to A, B, C, D, like this. Now the transpose of A actually takes the rows, like this is the row, right? Transform that row into column. So this is row 1. Transform row 1 into column 1. So it's like you take this row and you turn it, you put it in terms of column. And you take row 2, you turn it in terms of column 2. So row 1, so by like row 1, so like the transpose actually takes row 1 and convert it into column 1. Takes row 2, convert it into column 2. Okay, that's the job of the transpose function. Takes your row, turn it in terms of column. This row here in terms of column. Okay, so this is what we call a transpose of a matrix. The transpose, that's what it does. Now, when we say a matrix is a matrix, like let's see quick examples of that. Let's say I have a matrix A with entries 1, 4, 2, 5, 3, 6. A transpose is going to take this row here and turn it into a column. This row 1 becomes column 1. Row 2 here becomes column 2. Okay. Now the next one, let's look at another matrix B with entries negative 3, 4, 1, 2, 3, 2, 1, 2, 5. B transpose. We're going to take this row in terms of column, this row in terms of column, and this row in terms of column. Okay, so you take your row, turn it into a column, row, column, row, column. Okay. Now let's see another matrix C. Matrix C is gonna be 1, 2, 2, 3, like this. So I take the transpose of that matrix C. I take 1, 2, and I turn it in terms of column. 2, 3, I turn it in terms of column. So as you can see, matrix C here is the same. The values of C is like C is equal to C transpose. The entries of C and C transpose are the same, okay? But look at matrix A and its transpose. You can see that it's different, okay? Here we are dealing with a 2 by 3. Here we are dealing with a 3 by 2. Here is a 2 by 2 and the entries are the same. So whenever you have a matrix such that it's equal to its transpose, if a matrix such as C, like for the matrix C, matrix is equal to its transpose. Such a kind of matrix is called a symmetric matrix. So a matrix is symmetric if it is equal to its transpose. Okay. Okay. Let me go back to the notes. I think the time is over. It's unfortunate. It would have been very cool to finish it and give you a quiz next week. But anyway.
Again.
Yeah. So yeah. I think so yeah, so for A, B, this we had A, we had B, we found the product already. So I think and we had this matrix and that matrix. Oh, I think we haven't done this example. We are going to do it next week. So we stop here. We'll stop here. But we stop here at this part. We're going to continue next week. But the transfer of the matrix, the information is like in front here. We're talking about it more next week. Okay. So we'll stop here at this point, at this example. Okay, so let me take really quick the attendance and we're done for today.